Alright, completing printed circuit board design using Orcad capture and layout. We're just past figure 626, rigging of an electronic log transmission line. By T30NS, traveling edge for the raised edge, for the reach for the low, for the voltage for the low, is now the sum of the previous voltage plus the value of the incoming voltage, 4.7 volts plus reflected 4.7 times 0.9 equals 3.75 volts total, of 4.17 plus 3.75 is 7.92 volts. Reflected voltage 3.75 volts as well on the way back for itself. A T40NS for the rising edge of for the reflective of the lows beginning to arrive at the source for the RS voltage. The voltage source begins to rise, however, the strength of the impedance of the transmission line is greater than that of the source of the resistor. The negative reflection immediately heads back to the load. Reflection coefficient for the transmission line looking at RS is equal to P1000 negative 5 over P1050 equaling 0.9. At T of 50 NS for 37.5 volts reflective of the load, complete with the load resistor start with the voltage of the load side of the resistor source is sum of the original of the 4.175 volts incoming reflected volts of 3.75 volts plus the voltage being reflected back to the load for a total of 5.42 volts. And a negative 2.50 volts on its way to the load. At 60 NS, with a negative 2.5 volts reach for the lows, begin with the lower load voltage of the previous 7.92 volts because of the impedance mismatches between the transmission line and the load. Reflection immediately launched again with the reflection coefficient still with a positive 0.9. So the reflection of the same polarity incident wave with the incident wave is negative 2.5 volts from the reflected source, resistor source of the load with a reflected with the negative voltage added with the incoming of negative 2.5 volts into positive with the reflected negative voltage over voltage at loads 0.6 and 7. The drop significantly since P is higher than 0.9 volts. At T70NS, the negative 2.5 volts reflect the source completely with the resistor load, wherever the voltage from the original 7.92 volts incoming the voltage with the negative 2.7 volts reflected back to the load, and of course the negative 2.25 volts is on its way to the source. And then at 80 TA equals 80 NS, the negative voltage of it was reflected with the positively, leaving the sign intact for the load beginning with the arrive at the RS. Since the incoming voltage, negative voltage begins with the RS, begins to fall. Since there's still a negative reflection coefficient 0.23 thirds from transmission line through the RS, the value of it immediately begins with a bounce off of the RS is of the non-positive that heads back to the load. 9. At T90NS, the negative 2.25 volts reflected the load completely reached for the RS. Again, the voltage of the RS is sum of the previous to 5.42 volts, incoming the reflected voltage is negative 2.25 volts plus the voltage being reflected back to the load 0.67667 times negative 2.25 volts for a positive 1.5 volts and 5.42 volts plus negative 2.25 volts plus 1.5 volts is at a 4, 6, and 7 volt course of the 1.5 volts on its way to the load. Reflections continue back and forth, but decrease in value each trip the losses occur because of the energy is not reflected with each of the impedance interface absorbed into the source of the load resistors. Eventually, the reflection become too small to notice. We say that they have reached a steady state. With the time to reach a steady state is called the settling time, and the shorter the settling time, the better. Length of the trace of the L trace is much shorter than the length of the special extent of the LS, representing the rising edge of it will not fit the length of the trace will reach the driver before the driver even completely reached the steady state value. If the trace were reflective voltage were reflected many times, repeatedly fold back onto itself as the driver output climbs into the steady state value since the voltage and interference is. Some of the existing voltage incoming reflects and reflective reflection, and the effects of the reflection being smeared into each other. But by the time of the drive, with the fully reach of the fine value, most reflections have come and gone. Only the last smaller overshoots and undershoots evident. Figure 628 show what happens with when the PT time is much shorter than the R time. Electrical short with trace. The reflections occur with the previously described shown on the graph menu, with the reflection of the curve by the time of the reach of the full output level. Recall the voltage of each impedance of the interface of the sum of the previous voltage plus the incoming voltage plus the reflected voltage, since the reflections happen last relative to the rise time. Each reflection never has to chance to reach the full voltage and fraction of the rising edge at the time, so the reflections are as much smaller. Therefore, peaks, overshoots, and valleys, undershoots are also smaller, hardly noticeable, while the whatever output of the still rising end is also ring frequency is higher with a shorter trace. Alright, figure 620 shape with the negligible ringing of the electrical short trace. We have voltage levels from 0 to 9 in timing in seconds. Have second reflection, third reflection, fourth reflection, fifth reflection at voltage level. Alright, critical length. As mentioned above, with the electrical short trace is 1 over the propagation time with 1 over the half of the rise time. So you have the propagation time is equal to half of the rise time. The length of the trace is less than 1/2 of the special extent with the rising edge. The length of the trace is equal to 1/2 of the rising edge load of the SE. The length of the trace of the transmission line with distance just barely is called the critical length. It shows voltage levels and the reflections of the propagation time equals 1/2 of the rise time. Show the voltage with the critical length. The ringing still occur, but the peaks never level off, and reflections settle sooner. But again, 1/2 of the rule is limited with another goal. For example, determine the critical length of the design transmissions are given in the design section below in example 4 and chapter 9. Transmission line terminations. If it cannot make the rise time smaller with the and or length of the trace shorter, we will have the noticeable reflections and ringing. The only other way with the top of the reflections and ringing is to eliminate the impedance mismatch. They're called for the properly terminating the end of the transmission proper source and load resistors. We can make the RS is equal to Z over the RL. The resistors in the series of the 12 of the resistor and the parallel load. The impedance will also match that there are no reflections shown in figure 630. However, the 1/2 of the voltage drop of the load because of the voltage drop of the result of the resistor series is equal to the resistor load, so voltage load is equal to 1/2 the voltage drop of the load. The voltage load may not reach the logical threshold, preventing affected digital circuits from functioning. An alternative is to put the resistor in series with the driver such that the impedance of the transmission line C with the looking of the driver series with the resistors is equal to 0 So 0 is the source is 50 ohm driver output resistance at 10 ohm with the transmission line is matched with the driver putting a 40 ohm resistor in series with the resistor series. Example, the result is shown on the figure 31. Even the propagation time is half of the reside time. Only one reflection occurred with the flat section of voltage drop between 10 and 20 ns. If it's observed with the 40 resistor and when the resistor short of the resistor series with the reflection dies there. An advantage of the type of the termination technique is the voltage of the load is also much closer to the ideal voltage of the boundary with the voltage drive is usually not a problem, but it can be a problem with high-speed clock circuits for which the steady state of the on-off time is about the same duration as rise time. To match impedance between the source of the transmission line placed with the resistor series with the driver's such that the resistor series is equal to the source minus the resistor series. To match impedance between the transmission line and placed with the resistor and a parallel load with the R is parallel with the resistor load is equal time the source of the divided by resistor load minus the source. Printed circuit board routing topics. There are 4 areas of electrical consideration: routing PCBs, placing parts, PCB layers, stack up, bypass capacitors, and trace width, spacing width. Show 631 shows the reducing reflection resistor series with source. Part placement with electrical consideration. Alright, Chapter 5 addressed parts of the placement with the manufacturer in mind. We consider the part of the placement electrical performance in mind, usually with 2 goals complement each other, though occasionally they conflict. When conflict does occur, the attempt should be made with the resolve of the conflict in a way that is mutually beneficial. If there's no possible with electrical consideration, usually have the priority over the mechanical consideration, unless due to will result with a mechanical failure of the board. For example, that may be necessary to manipulate with the assembly of the soldering process, place parts on both sides of the board in order to meet the manufacturer's requirement. Most meet electrical performance requirements where a solution is closed over the PCB needs to manufacturer operation. Aside from the manufacturer goals, the first approach of the placing with electrical consideration, you will determine if the function of the circuit, especially true with the analog circuits, where a signal enters the PCB PCB with a file with a circuitry that is more and less than a single path with a concluding feeding back networks then leaves the board. Since analog circuits are suspectedly to have noise, the goal is usually to play with the parts minimum possibility with the degrading signals. Usually means keeping them as close together as possible so that the traces can be short possible to keeping the signal path straight as possible, and a zigzag back and forth, one from one side of the board to the other. The approach may be to increase the side of the board, however, it is not always possible. When digital circuits are desired to keep the related parts close together, the line short, but because the digital circuits often contain with many parallel paths with branches that may contain wide data buses, it may be nearly impossible to do so. Sometimes the best that can be accomplished is to keep the parts functional related closer together and place parts together with the highest speed clocks rise edges in order to minimize the length of the related signal lines. Mixed signal boards are even more challenging when both the analog digital circuits, high power circuits such as switching regulators, exist on the same board. In these cases, the printed circuit board should be segregated into the different areas shown in Figure 632. The topology may be varied, but the idea to keep the higher power other noisy circuitry closer to the connector if possible, with the limits of the return plane with the utilizing circuits there for minimizing the amount of return planes that is common between them and the rest of the circuitry. Digital analog circuits should also be kept apart from each other and minimize the effects of the switching noise. The analog circuitry with dividing PCB in this way, and it's usually necessary and beneficial to set up a split isolated plane layer shown in Figure 615. A Figure 632 board layout recommendation noisy circuit show the frequency power characteristics from low quietness, medium, high noisiest analog digital circuit type and connectors. The printed circuit board layer stack up. The printed circuit board layer stack up. Thickness is assigned by the manufacturer when the board is ordered during the routing process of the layout. With the PCB layer stack up thickness needs to be defined early with the design stage before working in the layout, since the stack up will determine how many layers will be enabled, how many power ground planes to establish. Strategy with the stacking on the PCB that depends on the number of types of things, such as the capacity of the board, manufactured circuitry, density, both routing and parts frequency, and analog rise and fall times, digital for signals, and the acceptable cost of the board. As circuits become more and more dense, additional routing and plane layers are required. Digital circuits commonly require more layers than the analog circuits, because the digital circuit is typically considered the grade of the numbers of the pin per chip, because of the higher number of the parallel interconnections. Higher speed circuits with the analog and digital may require a greater number of layers, even if they're not very dense. This is because the multi-layered boards can provide better for the impedance control shielding, since they have the additional ground plane with the more layer of the board at more cost. And once the PCB stacks up and the layer of the cost increases per layer, usually becomes for less additional layers to point. Additional benefits of shielding and impedance control considerably outweigh the increased cost of extra layers. There are many possible ways to design and stack up the board operated with low speed with an isolated environment, and almost everything you dream up will work. However, as single speed with increased with the layer stack up with the trace routings from between the increasing important because of the poorly designed stack up that can leave with the reflection exclusive of the electromagnetic interference radiation reflecting the external circuits, as well as causing self-inflicted crosstalk. The well-designed layer stack up the proper routing and not only minimize the energy it radiates, but also can make your circuit relatively immune from the external source of the radiation. Designs the layer stack up with only a few guidelines to follow, but they are important. The following few paragraphs example to demonstrate with guidelines. Since PCB for the construct with a double-sided core with the bonding together with a pre-preg with a multi-layer with a PCB that usually contains even the number of layers, odd layer boards can be made, but most of the cases they're not cost benefit of adding only one layer instead of a layer pair. If you need 5 layers, you may as well go with 6. Extra layer can also be extra return ground boundary for symmetry. Even the number of layers help minimize the board warpage. A single layer should always be adjacent and close to the plane layer, preferably the return of the ground plane with a minimized loop and induction with a minimized electromagnetic radiation crosstalk. Power plane should also be adjacent and close to the return plane that adds interplane with capacity, which helps minimize the power supply with the noise and radiation. If you have the choice between single player with a layer and between adjacent to the return plane, power plane being adjacent to the return plane, choose the single layer. You can add more bypasses and bulk capacitors between the power planes to make up the loss of interplane capacity. The following stack with example is offered with a reference only. There are many more with a combination of possible, but only fewer is shown with a plate with a reference of additional example of detail. Final board thickness example is 0.93 thousandths of an inch of the copper with 1 ounce thick of of availability. Certain dimension will depend on the manufacturer's capabilities of the process. Thickness listed in the figures are given to provide perspective. You can use table 4, 3, 4, 4, 4, 5. Get an idea of different combination cores, pre-preg types used to make the different layer thickness. Remember, the thickness from the tables are all pre-assembled thickness, with the finished thickness may vary since the trace is the sink and the soft pre-preg, while the plain layers do not. And so, with advanced circuit website, for example, layer width thickness. A signal return concurrent will be on the ground or power plane with the closest signal line, if it's possible, relative to the dimension determine the trace plane. Routing pairs of the daily all return current circuits will need to end up with the ground return pin with a per PCB port connection. Power connector if the beneficial stack up the return of the PCB to try to make it easier for the return currents for the critical high-speed traces to be paired up with a certain ground plane so that they were not forced through capacitor leads for Viva to go back with the ultimate return point, for there's no guaranteeing that they will follow it. But remember that an AC signal, there is no difference between the power plane and the ground plane because they are shorted together with the bulk of the bypass capacitor. So when the signal trace transition of the one layer to another, the return current circuit may not have the easy path from one ground plane to another may chain with the return source of the power plane until they have the convenient path back to the preferred ground plane through the bypass capacitor of the return current that is now flowing on with the preferred plane. Impedance of the transmission line can significantly different from what they expected to sit for the return circuit stating with a single line with when it changed the layer of the return current bridge is installed with using 3 Vivas connected with the ground planes and the work capacitors with fan out with the Viva near the Viva the transition signals one layer to another. Right, there are several symbols within the that define with regard to the check-up of the figures. H of the figure implied with a horizontal rounding, V for vertical rounding, and some of the figures with the R usually implied with the non-specific routing directions, concentration routing strategies. This horizontal and vertical direction make the routing process more efficient. High density design reduce the number of the V that required for the complete with the connection to the HS is used the high speed signal. They usually buried between the plane layers and an extra shield with the ground label GENT symbol is just represented the ground return plane for the single power of the symbol of the PR or PR positive and negative represents any power plane such as the 5 volt constant current of the digital circuit plus positive volt negative volt analog circuit. These 3 basic for the transmission line, microstrip, strip line, and the coplanar may be not always for the need for the transmission line, but no matter how you route your board, one of these types of the representing the need is not close with the resemblance of the types of transmission line configuration can be realized with the other type of tackle of which are not shown here, as in will depend on the capabilities process with your board manufacturer. Figure 6.3 shows the 3 different 4-layer stack up identical with thickness this in mils. Figure 6.3a, one of the most common 4-layer stack up with some of the digital analog PCB with the lamp pattern traces that are placed on the outside with the top of the bottom of the board and power of the return plane to the inside place from the tray with the outside with enable the post-fabrication inspection troubleshoot. Figure 633B, 633C play with the power of the return planes outside of the board with the tray for the inside of the arrangement, help with the shield with the trace of the outside of electromagnetic interference, and helps contain self-generated radiation between the planes consequently minimize radiation with the electromagnetic interference configuration. 633C can be used with the route low density analog circuits that require positive and negative voltage, dually supply op amps, and powers routed to the amplifiers which wide traces or copper port shares layers using routing signals. So 633 show the typical 4-stack layups. You have the high voltage, high ground power voltage, core pre-peg, surface microstrip, ground high voltage power, pre-peg, core preg, and then you have ground high power, voltage power, ground. Figure 634 shows an example of 6-layer PCB stack up with the figure 634A with a typical stack with a stack up. Typical stack up with the digital circuit with the analog circuit with the do not require with the dual power supplies. The arrangement provides 4 routing layers. The 2 plane layers in a routing layer can be used for the higher speed signals since they are shielded with the ground and power plane, but the analog circuit is required with the dual power planes. Stack up figure 634B provides highly functional stack up with the 2 following routing layers. So let's look at, A has a surface microstrip, stripline, asymmetrics, and working in with a pre-preg to a 3 out of 5 pre-preg, 2 cores, high ground voltage, high ground power voltage. Then B with B, 3 preg, 2 core, R ground ground PR and R, negative PR and ground R, surface strip, microstrip, the semi strip is the line asymmetric, surface microstrip, ground HSI, high ground power, HS voltage ground, core preg, strip balance, line balance. Alright, functional stack up of the two following routing layers, two partial routing layers, share layers of the power pod with the power negative layers, ground planes with adjacent all signal power layer that provides shield with the inner signal trace. Alternately, with the shared power with the routing layers can be dedicated with the power only, but the limits of the board to two routing layers with the stack up with the figure 634C for the two well shield with the balanced strip line routing layers, highly speed with the digital circuit adjacent ground planes for each of the signal power layers and limitation stack up there is only two routine routing layers. Figures 635 and 636 show the example of the 8 and 10 layer stack with respectively only a few examples shown, but by using the different stack up strategy with the previous example, the capitalizing on the various finished board thickness available, the most board manufacturer can be seen with a higher layer stick up to provide with the multiple routing pairings. Alright, in this first one on the A, you see a preg, core, preg, and that was high power ground voltage, high ground power and voltage. With a surface microstrip and strip line SS remains in the middle. And then B would be grounds on the outside, then HSV, and then another ground with a HSV, HV power, and then it has core preg, strip balance line, asymmetrics on the bottom. Figure 636, the 10 layer pack up, the cores on the outside, and then pregs, and then core, and then pregs, and inner core. And those are surface microstrips on the outside, and then strip line asymmetrics for your pre-pegs, and then H ground, HS, power ground, HS, ground voltage. Alright, bicapacitor fan out. Bicapacitor will serve the two main functions, beginning with a short high frequency noise of the ground to act with the current server reservoir. Consequently, there are two basic methods of fanning out with the power pins. First method to route the power pin bypass capacitor before with the fan out V with the power plane, figure 637 and A show. The second method is to route with the power plane flares, placing the fan out between power pin and the bypass connector shown figure 637 and B with the configuration 637 and B can also be realized with a shared Viva that is shown in or when integrated circuit in the capacitor have their own Vivas. First glance may appear with no difference electrical speaking, with the difference of the significant high frequency fast rise times. Additional with the other issue with the method of the assembly, wave and reflow, soldering, available board, real estate, influence, orientation, routing of bypass capacitor, source literature do not always agree with the best method, but often figure 637A is recommended for the analog circuits, 637B for the digital circuits. Alright, 637 is over the power pin out methodology. A is the power pin by bypass connector to Viva. Integrated circuits from the bypass capacitor to the Viva power plane and ground plane. And then integrated circuit from the power pin to bypass connector, and that goes to the power plane, and then bypass connector and the bypass ground plane. And that's fanning out. Trace width of the current carrying capability. With the current flow of the conductor will heat up the amps squared over the ohms losses. While wider traces exhibit the less resistance, therefore less heating. To determine the minimum trace width required with the minimized heating to determine the maximum current trace will carry the thickness of the copper. You will use the board if it uses equation 17. Calculate minimum trace width, where W is the minimum trace width, with H is the thickness of the copper cladding in ounces a foot squared. Amps is current load of the trace, and amps K is the use for the inner layers and used outer layers, top and bottom layers, and then triangle T is the max permissible to arrive at the temperature of the conductor above ambient temperature. You can also see the graph shown in the figure 638 with the derive of the curves of the institute printed circuits 2221A. And then it shows a picture of the minimum trace width of mils over the trace current amps, and then the notes. You can usually use any of the sharing technology for the most signal application. Figure 638 shows the minimum trace width of 1 ounce inner the outer layer copper with a temperature of 10 degrees Celsius with a 6 mil tray with a run up to 300 milliamps. on the inner trace, about 600 milliamps on the outer tray. For the manufacturer reliability consideration should be used as wide as practical. Usually applications concerned with the power supply lines for large circuit power supply boards in general. Trace width of the control impedance. Controlled impedance of the PCB, but it can be significantly more expensive than standard process for the PCBs. But before going through the effort and experiment with the design control of the impedance of the transmission line with the PCB, it's a good idea to determine that if they need and by determining the traces with electrically long whether the control of the impedance is required. The digital system minimum with a propagation time to be left with the rise time. The drive of the propagation time is half of the rise time. The rise time and the double is greater than 2 per propagation time. And the discussion reflection of looking back with the length of the length trace should be less than 1/2 the special extent with the edge diff and rising edge diff. The length trace over the length of the edge or else SE edge 2 times length trace. Determine the condition if you need the return of the rise time over the propagation time per rise time or the fall time. And the fall time can be obtained from the dash sheet with the device driving the traces. Trace will have units of the time. No single bolt of the rise and fall times must fall within the limit. Smaller value which should be used in calculation rise time, fall time. Several logical families listed in Appendix D. Calculate propagation time. You will need an intrinsic propagation delay, which units of the time to display distance. Intrinsic propagation delay with the various transmission line configurations given in Table 6.7 and 6.6 and 6.7. And gives you these pictures, these tables, the 6.7a strip line and transmission line configuration. Next, calculate the propagation time. Propagation time, you have the equation 18. Propagation time is the work of the length trace over the TPD with the propagation time traces 1 with the propagation time of the length of the trace measured on the PCB with towards the times the intrinsic propagation delay with the table 6 and 6.7. If determined the trace electronically too long and neither to be shortened or impediment need to be mapped to determine the maximum allowable tracing with the equation 19. Since propagation time is half of the rise time and the propagation time is equal to the length trace times the intrinsic delay time. So the length of trace is less than the rise time over the 2 times the intrinsic propagation delay. Analog system determine the critical length of the trace, the respective wavelength, rather the rising edge wavelength is determined as equation. Wavelength is equal to the intrinsic velocity over the frequency with the signal of the trace. Various traces lengths of stay in the literature anywhere with the length trace of half the 6 wavelength times the length trace of the half or greater than 1/20 of the wave. The IPC 2251 recommended with the length trace of the be less than 1/15 the wave where length trace of the length of the trace is measured with the PCB with the wavelength highest frequency component of the signal shortest wavelength. Figure 6.6 and 6.7 as you determine the propagation delay when the PS in inches. Critical length calculation analog digital circuit to be determined in the equation 1920 with the trace critical electrical long source of the load resistance transmission line impedance needed to be controlled with the design control impedance of the transmission line. The PCB the table 6.6 and 6.7 to determine the trace width inches of the trace thickness as ounces and foot square. Dielectrical thickness with an H mils and dielectrical constant unit list to determine on your board manufacturer. This is another transmission is not in the table 2, table 6.6 and 6.7. The coplanar transmission shown figure 639. Typical distance over thickness in mils relative to the width of trace width compared to the other configuration. Copper along each side of the trace, the top side return plane, typically less than the 5 trace width both direction. Bottom side return plane is not present in some applications. Alright, fix 39 show for the coplanar transmission line with height, distance, and thickness. Equations for the documented literature of this type of the coplanar configuration and the except of the transmission line design handbook by Brian C. Waddell. Equations are not presented here because of the readily unwieldy type of the transmission line is not widely used in FR14 S4. If you need this type, leave the reference for the full description of design, even the limitation approximate type of the configuration. Sometimes there are attempts to use the guard trace with the copper pores because of the relative dimension of the equal to the height over the distance of the height is approximately the distance accident design. So for the microstrip is usually a result. Trace space the voltage withstand with artery of the control spacing between traces of the one to ensure the adequate voltage with withstand capability, insulation resistance between high voltage lines, and 2, minimize crosstalk between signal lines. Table 6.8 show the abridged version and similar table of the IP Institute circuit board 2221A. Table 6.1 show the required trace spacing with the various voltage range, internal external layers, spacing the external trace that depends on both of the voltage and external coating of the board. Figure 6A show the minimum conductor spacing in mils, and show the voltage between conductors, internal trace of the bare and external traces, solder mask, bare, and conformal coating. Trace space with the minimized crosstalk, the 3 width rule, the tracing spacing with the length of the shown is in 640A of the wedge edge to edge spacing between the traces, typically 1 conductor width. If the trace is suspected with the crosstalk, with the adjacent traces should be kept at the minimum with 2 trace wedge edge to edge. From other traces shown in figure 640B, the referred to as in the reference as the 3 width rule because of the center spacing with the 3 width rule, and indicate figure 640B a 3 width rule with the trace with the out of reach of 70% each for the magnetic field. If the trace with the controlled impedance transmission line with a reasonable approximation, keep the traces 10 width apart. The center lines will keep the traces about 98% each other's out of the 98% each other the field. Figure 640 show the trace spacing, when the typical spacing, and then 3 width spacing to minimize cross talk. To adjust the trace to trace spacing layout, go to option global spacing display with the route spacing spreadsheet. Figure 641. Double click with the track to track and column header. Enter for the edge to edge spacing in the box and click OK. Traces with acute or 90-degree angles, route frequency, analog, high-speed digital traces with acute with 90-degree angles have been discouraged by everyone anywhere. Everyone agrees. Not everyone agrees anymore on how much problem it really is. The argument is that the trace width increased with the factor of 1.414. Corner trace, as shown in figure 642, with the cover of the chain with the resistor characteristic compatible with the increase of the capacitance D with the trace for the discussed above with the demonstrate with the chapter 11 impediment of the mismatch for the cover of the reflection steering cover of the ring digital circuit is fast with the right time standing traveling ways high frequency analog circuit in theory with a 90-degree corner should be avoided at least when the routing control with impedance transmission lines. 642 show for the tracing geometry with a 90-degree turn. You have 2 12-inch parallel lines at perpendicular 90 degrees at 6.97. A look through the reference show for the high-end network analyze with the time the domain reflector meters measure for the reflection of the 90-degree corner effect with the evident however the frequency of the reflection occur with the high upper G's GH gig frequent GH's trace greater than 50 mil wide and TH for the trace less than 9 mils paired with the other show for the impediment of the discontinuous such of the V is to the effect of the other insignificant. Another thing to consider is what the layout anyway with the conductor. Corners are not sharp with the shown with the figure 642 with the recall with the chapter 1 with the pad tree with the drawn with the flash draws. Respectively, photo apply with the aperture for the given in the diameter with the square aperture for the B with an additional square pad with the layout even the brown apertures tray for the Gerber code with the 90-degree corner reduced the layout and shown figure 643A. Although the corner may look fairly sharp, close to the corner shown figure 43B show the outer edge of the round only with the inner core with the square with the result of the small increase with the width for the square corner. Difference between a 12 mil tray, 17 mil tray with the sharp corner, 642 is about 11.5 ohms dielectric constance with the 4.2 with the core thickness, 10 mil with the difference between 612 mil tray with the 14.5 mil tray. Rounded corner in figure 643 is about 6.2 ohms. However, the effect of the extra width for the chain with the impedance is very small. X is shown figure 643B with a 7.73 mil squared for 12 mil tray with the equivalent area is divided by 2 each piece for the placed on either side of the straight segment of the 12 mil trace as indicated with the arrow in chapter figure 644. Clear with the X of the grave with the 90-degree corner is insignificant compared with the factor of the V of the land pair with the V is shown and with the figure with the V1 VIA1 from one bet any technology file. Literature Brooks page 385 suggests the acute angles of 135 could be used about 1 gigahertz and shows in 643 a geometry corner 90-degree layout. You have your 90-degree camera cord and your chamfered corners and excess copper and 90-degree corner. So this is the excess would be the inside of the outside in the edge. Figure 644, excess compared to the typical Viva. Chapter 7, making, edit, and capture parts.